All right, everyone. Welcome to the fifth and final day of our Tackling Climate Change with Machine Learning workshop, today focused on cross-cutting methods in machine learning with wide applicability across climate change mitigation and adaptation domains. So, as I mentioned, this is the fifth of our 5-day workshop. So previous days were focused on energy, land use, climate science, and adaptation. And we also had a main workshop on the 26th focused on a wide variety of themes. And so today, hopefully, is a day to sort of tie together a lot of the applications that were talked about in these previous days and really focus on methodological innovations that are required from the machine learning side in order to push some of these applications forward. So the participation today hopefully is straightforward for those of you who have joined for previous days, but basically join the Zoom meeting here. Awesome job, you're here. And ask questions in the Zoom chat. All of the sessions will have some amount of talking from the speakers, and then we will have time at adequate time basically to ask questions to the speakers. So please feel free to be posting those in the chat throughout. So this workshop could not have come together without a whole lot of organizers. And so just wanted to thank the organizers of the main workshop and this virtual booth day. So in particular for today, David Rolnick, Lynn Cox, Sasha Lucioni, Chris Shankar, and Sharon Zhu, as well as co-organizers and a program committee that reviewed all of the submissions for this particular workshop. And I'd also like to thank our sponsors, Microsoft and DeepMind. So for a full schedule of today's workshop, please visit the workshop website, whose link is on this slide. We also have a hashtag for social media for those who want to tweet about the workshop. And if you have any questions or issues sort of with the technical aspects of the webinar or anything like that, please feel free to shoot us an email at climatechangeai.iclear2020@gmail.com. And for those of you who are registered for iClear, you can also message us in the Rocket chat. So just to go through a brief overview of today's schedule. So we'll be starting with a discussion of forecasting, which is a really relevant technique across areas, including transportation, buildings, water, climate science, and so on and so forth. So we'll hear from a variety of speakers who are working in these different areas. We'll then have a talk from Zico Coulter about hybrid physical modeling, specifically how we can incorporate physics and hard constraints into deep learning models. We'll then have a tutorial on climate change, specifically geared towards those working in machine learning by Lynn Koch, Chris Shankar, and myself. Next, a session on accelerated science and engineering and how machine learning can speed up the discovery of, for example, next generation batteries, next generation solar panels, or nuclear fusion. These are the 3 topics discussed in that session. And then finally, we'll end with a fireside chat on remote sensing and artificial intelligence, where remote sensing is commonly used to gather important information that's necessary to make decisions across many climate change domains. So with that, I'm going to hand it over to today's speakers, the first session being forecasting. So Lynn and Chris, take it away.
Okay, thank you for the introduction, Priya. And thank you everyone for joining. Really excited for this panel on forecasting. So the ability to anticipate the future is key to a variety of efforts to control emissions and to prepare for the impacts of climate change. It seems fitting to begin our cross-cutting methods day with a discussion of forecasting techniques, their deployment, and their current limitations. We're lucky to have Kristina Orehounig, Lloyd Treinish, Yan Liu, and Henry Martin on our panel today. In the first part of this panel, each speaker will share a short introduction to their work. For the remainder of the hour, we'll have a group discussion drawing from questions that you enter into the chat. So if there are any questions that come up either during the introductions or while people are speaking, just enter into the chat and we'll read them off during the panel. So without further delay, Kristina, if you're ready to share your screen, your presentation. Okay, and Kristina Orehounig is the head of the Laboratory of Urban Energy Systems at Empa, which is the Swiss Federal Laboratory for Materials Science and Technology. Her work advances the modeling of energy demand in buildings and by this helps decarbonize the building sector. Next, Lloyd, are you ready to set up? Share your screen. Okay. Lloyd Treinish is Chief Scientist in Environmental Modeling, Climate, Weather, and Deep Thunder at the IBM Watson Research Center. He heads the Atmospheric Sciences Research Group with a focus on weather, water, and climate. So whenever you're ready.
Okay, now I'm okay, and I'm hoping you can see the screen. Yep. Okay, great. Let me get started. So it's a pleasure to be here, and just as what you see in the background is an animation from colleagues from NASA that showing global surface temperature changing. These are the anomalies compared to a 30-year baseline from 1951 to 1980. But it shows how our planet is warming. And these type of data are derived from models, physical models of the atmosphere in combination with observations, and which sort of will lead to a couple points I'll be making shortly. And one thing also, some of our experience in looking at climate-related issues and impacts does connect to experience in weather, but we need to be clear that climate and weather are not the same thing. And I often like this quote attributed to Edward Lorenz from more than a half a century ago about the nature of climate. And he's mentioned this more than once. And as you may know, many of the ideas around chaos and chaos theory were derived from his early work looking at trying to model weather systems. And one of the things that we're trying to look at IBM Research is coming from the perspective of, so no matter what we do, and even when we think about the pause and positive environmental impacts coming out of the COVID-19 situation, our planet's going to continue to warm. And so we need to understand how to look at the impacts associated with what is happening from climate change, independently of pursuing policies to reduce those emissions. And so for some of our work at IBM Research, we're focused on trying to understand the effectiveness of strategies associated with dealing with the fact that the planet is continuing to warm, and by looking at the local impacts of climate change. And we see this across a number of different industries, pretty much most industries. As you can imagine, there are first order and second order effects. And the way we think about this is with sort of a simple taxonomy, but in a way that is derived from some of our long experience and really related to weather, in terms of how to really connect decision-making to information about the physical environmental state, in this case, climate. But climate introduces a number of challenges in looking at this. So one way we think about it is trying to do this sort of decomposition. Ultimately, we start from what's required from the business side, and by business, that doesn't necessarily mean commercial. I mean, that can be, of course, governments, nonprofits, etc. But the concept is trying to get an understanding from the decision maker's perspective of what information is actually needed. And this turns out to be a challenge on a climate scale, because in many industries, they've not even considered how to look at what's a future state of my assets or my citizens, 10, 20, 30 years ahead. Often it's difficult to even conceive of what to address 12 months from now. But the way we like to think about the problem and decomposing it is where we need to have an understanding in a probabilistic way of the state of the future climate. And so we use a combination of both physical and machine learning methods in order to address that. The physics is fundamental to understand what the current climate state, but because of the knowns, both known and unknowns associated with this and inherent uncertainty, these all must be probabilistic. And then we would drive that by trying to translate a representation of the physical world, into impacts. And then that also then is driven by machine learning methods. And these probabilistic estimates of these effects are then ultimately what's needed for decision making. And in some sense, where we get these ideas from the weather perspective is that often for decision making, weather information, even if you're making a decision about what might happen tomorrow, it's not about what the weather actually is, it's what those impacts are. So, in a simplistic way, you could look at a precipitation forecast and decide, should I take an umbrella tomorrow? But really what you're after is, am I going to get wet or not? And so we want to translate those simple notions into these more complex aspects for long-term decision-making to understand the effects of decisions being made now on potentially decades ahead. And we see this in a number of interesting applications. So for example, the previous speaker had referenced about renewable energy. One thing that we see in the design and deployment of renewable energy systems is the future climate state generally is not included in their design. So that is location and the potential for power prediction over the, let's say, 20 to 30 year lifetime of that, let's say that of a solar farm, for example, is not included. And those are changes that we see as being necessary to make more effective planning. And we see this in other aspects. So for example, looking at the resiliency of an infrastructure for cities, how valid is the plans for improving that resilience? And often these sorts of plans are based on the most recent weather-related disasters, not necessarily on the future climate. And we see this in a number, and the previous speaker had brought up connections to buildings. So one element that we also see related to that is understanding the energy demand from those buildings or the heat generated by those buildings and the interaction with the atmosphere. And how can we look at that in light of a changing climate, for example, to reduce energy usage or to mitigate the impact of heat waves? And then we're beginning to look at more complex relationships when we now think about, for example, impacts on food supply and the connections to available water and energy to drive that, all of which are being exacerbated by a changing climate. So let me conclude there, and hopefully that will provoke some questions from the audience. Thank you.
Okay, thank you so much for that introduction. Our next speaker is Sarah Fletcher. She's an incoming assistant professor at Stanford studying water resources and climate change adaptation from a socio-technical systems perspective. Her work integrates methods from hydrology, policy analysis, and data science to inform decision-making around critical environmental challenges. So whenever you're ready, Sarah.
There we go. Hi, everyone. My name is Sarah Fletcher. It's really a pleasure to be here speaking with you today. Thanks for having me. My work focuses on water resources planning under uncertainty with a focus on climate adaptation. So I'll talk a little bit about kind of an overview of the field and my work and the role that forecasting plays in this. So what do I mean by water resources planning? This is kind of an overview of really what this field is. It's providing decision support for river basin or watershed planning. So we can think about this as we have a river basin or a watershed, and we have a whole bunch of different competing end users and end uses for this water. We have farms, we have industry, we have cities, and we have to leave some water for the environment. And the challenge in this discipline is that there's a huge amount of uncertainty and variability in how much water is going to be available in the future. And that variability is at the daily time scale, monthly, seasonally, annually, sometimes decadally. And now as we have climate change, we're going to be in in new places and really having to figure out kind of how these systems are going to be changing in the future, both on the water availability side and then also on the demand, how all of these different end uses are going to change and how the interactions and trade-offs will evolve going forward. So as a systems modeler, this is the type. Here we go. As a systems modeler, this is the type of framework that we often use to provide decision support for these types of tools. So kind of following on from what Lloyd was saying in the previous talk, that we use these climate models and we downscale them to a particular regional hydrologic system. And then we look at how these hydrological flows interact with the human system and the land use and water withdrawals that we have. And so there's kind of forecasting that happens in all of these pieces. And then one kind of new emerging area that I've been exploring is in looking at the role of forecasting in how we control and operate and manage the water system. So what are the human interventions that we're doing, and how can we think about predicting how those human interventions will have impacts back on the environmental system? So there is a long history of using methods from control theory and things like reservoir operations, and now more and more methods from machine learning and reinforcement learning in operating these systems as well. But this is really kind of put to a challenge when we're talking about climate change, and can these methods really be extended to looking at multi-decadal decision making? So the way that I really think about this is that we need to tailor the forecasting and decision-making approaches that we use to the type of decisions that we're talking about. And so the decisions that we use in water resources range from operations and management all the way to public policy and infrastructure development. And these operate over a wide range of timescales from the daily all the way to multi-decadal. And as we increase the timescale, we typically have more irreversible decisions. We're making infrastructure decisions today that are going to be around for many decades. And also the uncertainty gets much larger. In many places, 3 decades into the future, we don't know whether the climate is going to be wetter or drier in a particular place. And so this means that in the short term, there's really a lot of opportunity to do really high quality real-time forecasting, reinforcement learning, et cetera. But then in the long term, we really have to be aware of the limits to our ability to forecast and focus on developing solutions that are robust to many outcomes and adaptable to surprises. And so a challenge that I've been working on a bit is kind of how to bridge this gap in the middle, and how to think about making decisions today, like infrastructure development, that are going to be around for a long period of time. So I'll just show you kind of one example from my work on that. So this is some climate projections from a location in Kenya, where you can see that decades into the future, we don't even know whether it's going to get wetter or drier. So there's a really wide range projected by climate models here. But what I've been able to do in my work is recognize that, okay, maybe we have a lot of uncertainties today, but as we collect new observations about how precipitation is changing in the future, we'll be able to narrow in the range that we expect in the future as we collect more information. And so if perhaps we saw a wetter climate, we might be able to know that we have a lot more precipitation in the future, versus maybe here's another kind of drier climate that we might get. And so these confidence intervals here are developed using Bayesian estimates that allow us to estimate what our potential to learn in the future is versus kind of what is the amount of irreducible uncertainty that we have in the system. And then this is really powerful because we can actually take these uncertainty estimates, put them back into a decision support system that allows us to say, well, what are all the ranges of precipitation observations that we might have in the future, and what does that mean in terms of the infrastructure that we have today? And that allows us to develop these kind of more adaptive infrastructure approaches that can take into account opportunities to learn about uncertainty in the future. So that's just a really quick overview, and I'll save a lot of time for a discussion, and looking forward to connecting.
Thank you so much for that introduction. It's really interesting starting to see some themes already emerging. Our next speaker is Yan Liu. She is an associate professor in the computer science department at USC and the director of the university's machine learning center. Her research interests include machine learning and data mining, including applications to climate science and mobility. So whenever you're ready.
Hi, everyone. Good morning. Thanks a lot for having me in this exciting workshop. Today, I'm just going to spend a few minutes to talk a little bit some of the interesting research efforts we made recently on interpretable deep learning models for forecasting. Obviously, before that, I also want to give a quick overview in terms of what we have done in the past 10 years. So basically that our main research efforts is developing novel machine learning model for analyzing and predicting time series data. And our application, right, is actually starting with climate change and then later developed into many other areas such as traffic, power grid, healthcare, and etc. And then when we look at in terms of the specific applications, we try to make sure that we consider the special properties of each application, but at the same time leveraging recent advances in statistics, economics, theoretical computer science, and many others in order to develop the most appropriate model. Here are just some examples. For example, we have developed the Gringer graphical model, functional data analysis, point process, and stuff like that. So next, I'm just going to highlight two major work along this line. So the first work is actually where get me started. Well, I was working as a researcher in IBM Research. Actually, my colleague Lloyd just presented the work on climate. And this is also started where I am in terms of now developing novel machine learning models. The basic idea in there is that given the time series data, where we try to basically understand how the different time series affect each other. That is whether a particular time series will be useful in predicting other time series. And then we developed the so-called Gringer graphical model so that we'll be able to uncover the temporal dependencies between multivariate time series data. And there we will be able to apply it to address some of the most critical challenges in the society, including the climate change attribution and also some in the immune gene regulatory network analysis. So we have all the code visualization tutorial available in case that you're interested. Another line of research work that we did after working on understanding the data is actually for modeling and forecasting. It is known that all these spatial modeling tools built on statistical models such as grading or Gaussian process models suffer from major computational cost. In our previous work in the past few years, we started a line of research on using the tensor-based approaches where we will be able to actually use the low-rank tensor regression to achieve very much similar prediction performance as the Gaussian process model and others. We applied it to climate modeling and social network analysis, got very encouraging results. You may be wondering why such a simple model would work really well. This is actually recovered in, reviewed, actually the insights was reviewed in one of our AISS paper where we have proved actually the tensor-based approach that we developed will correspond to Gaussian process, but with a piecewise linear kernel. In other words, that we want the kernel, the Gaussian process with the kernel to learn automatically. Well, for Gaussian process, you have to basically design the kernel. If you're interested, these are lists of the publications that we had before. Obviously that things move fast and everybody knows about deep learning. That is all the major theme in the whole ICLR conferences. Our research work also moved forward from that perspective. And specifically, we work on the traffic prediction application where we noticed that a large amount of data are public available, but at the same time, there's a lot of challenges in terms of when predicting congestions or accidents. And then because of the chaotic nature of the accident and also non-stationality of the time series and much of the engineering, feature engineering have to be developed. And therefore that some specific deep learning model may be able to actually help in that from that perspective. And that's actually started our journey for deep learning for time series forecasting. Given the interest of the time, I probably won't have to go over everything, but I want to draw your attention to a particular paper that we published 2 years ago in here. We call this as the diffusion convolutional recurrent neural network. The basic idea is that we try to model the road network in traffic application using the graph. And then we want to use the convolution layer to capture the subnetwork of the row network. And then at the same time, we also will be able to capture the bidirectional traffic flow, so that we'll be able to better estimate or forecasting the traffic. So if you're interested, definitely check out the paper. But basically across the board, our model were able to achieve the best performance when we compare with the state-of-art methods in terms of both the traditional methods and also other deep learning models. And then the last thing that I want to touch, also the basic theme of what I was starting at the beginning, is that we think that deep learning model is really a black box model, and it's really challenging for domain experts to actually fully utilize whatever that we actually build for forecasting model. And therefore, our endeavor started about 2 or 3 years ago, where we try to decipher what is going on inside the deep neural network model. Many different type of approaches have been developed for interpretable deep learning model. Obviously, the main goal in there is that we want a relatively interpretable model, but at the same time, we try to achieve similar prediction performance as a neural network. And here is just some of the previous work people have been working on in terms of direct interpretation and indirect interpretation. Some of the work that you probably are aware of is, for example, the LIME approach, which actually use the locally weighted linear regression for local interpretation. Or in this direct interpretation, basically directly estimating the feature importance from the network weights. Our approach is a little bit different, basically that we want to actually capture the feature interactions. And how do we define the feature interaction? We call them as non-additive grouping of variables and functions. Here's a simple example. For example, the fundamental, let's say the ground truth function f1x involve 10 different variables. And then when we look at the specific ground truth function, we notice that actually there are 4 different interaction sets. For example, the first term involving x1, x2, and x3. And the second one is just one feature, therefore no need to worry about it. And then the third one is x3 and x5 and stuff like that. So recovering the feature interaction set extremely important, because it recovers basically what the deep neural network is able to capture in terms of revealing the underlying ground truth function. And the second one is that once we recover the feature interaction set, we'll be able to actually build a very relatively, I would say that a simpler model, so that we'll be able to achieve similar prediction performance as the neural network model. So this is actually what we achieved in this iClear paper, also published 2 years ago. With the interest of the time, I would say that I'm just going to give you a very highlight overview. We started our work in that paper on feed-forward neural network. And given the publication in Europe's following year and also in iClear this year, we also extended to convolution neural network, graph neural network, and stuff like that. But basically for the simple feed-forward neural network, what we're trying to do is that we're trying to study the weights that we learned from the feed-forward neural network. One important observation that we notice is that any input feature, if they interact with each other, they must actually follow a strongly connected weights to a common hidden units. And for example, in here, for the F1 that function that we had before, we're saying that if the neural network is building a really strong model, then it means that it must capture the interaction between X1 and X3 in some common latent nodes. And then our job is trying to recover all the feature interactions by examining the feature weights we learned from a sparse feed-forward neural network, and then we'll be able to review interesting insights. Some theories in there, and then this is our proposed algorithm. But the basic idea is one of the important things we want to come up with is that we need to define what is the interaction strength for each hidden units. And this basically consists of two parts. One is approximation of this particular hidden units to the final prediction. And we can use this to actually the ways to product of these ways to propagate the influence from that particular node up to the final prediction. And the second part is obviously in terms of the weights, the individual features to that latent features. And in there, we actually use the minimum operator. Without too much of the detail, this is the minimum operator. Without too much of the overview of this part, I would say finally what we were able to achieve is that we're able to actually get the feature interaction set. At the same time, afterwards, we'll be able to actually get a generalized additive model where each particular additive term will consist of a smaller neural network with concern only the subset of the interaction sets that we uncovered. And in the end, we were able to actually uncover very useful two pieces of information. One is that given the ground truth function, we will be able to uncover all the interaction set. For example, compared with the state of art, we will be able to actually uncover all the interaction sets much more efficiently, both for pairwise interaction and also for higher order interaction. And then the other one is that when we look at our prediction results, where we can't see in here, but in the paper we show that once we recover the interaction set, build a new, simpler generalized additive model, the prediction results pretty much similar as what we had before. So with that, I would like to just stop to say that deep neural network definitely provide a lot of research interest for us, but I would say that giving the insights for the domain experts and working with them together to understand the model would be really an important future direction for us. Thank you.
Thank you very much for that introduction. Sorry that we don't have more time to go into all the details here, but I think these are some great resources to be sharing with the community. Our final speaker is Henry Martin. He is a PhD student at the Institute of Cartography and Geoinformation at ETH Zurich in the Mobility Information Engineering Lab. His work focuses on machine learning and transportation, and he won second place at the 2019 Traffic Forecast in Europe's competition with his team.
Yeah, thank you. Yeah, thank you very much. I'm a PhD student at the Mobility Information Engineering Lab. You can see our lab in the overview here. And I just want to very quickly give you two ideas where forecasting is important in human mobility applications and how these relate to climate change. So we are a geoinformation science group that is a niche science that focuses on spatial data science, if you want, how you would call it today, probably. I started in 2007, and the main goal of our lab is to develop computational methods that are tailored to human mobility applications and problems. And in my mindset and my work, I'm very much influenced by the energy sector. So before I started in the mobility and transport sector, I did mostly research and lectures in the energy sector, and I'm really amazed by the success stories of renewable energies. So over the last 10 years, I would say, all over the world, they basically exploded. And many countries today have very realistic plans for an energy transition within the next, let's say, 50 years. And we are no longer debating if we want to do the energy transition and have energy generation only based on renewable energies, but when we want to do it and how we do it and how fast are we doing it. So I think this is a great success. And as you can see on this next slide, this success does not relate to the transport sector. So here you have for the European Union, the greenhouse gas emissions development over the last 20 years over different sectors. And you can see that the transport sector is clearly lagging behind the other sectors. And why is that? I think that the energy sector was extremely successful, but it was also very, very easy for the individual, because the individual didn't really need to change his or her behavior. because even though you build wind parks and solar power and it's very complicated to plan all of this, you can just continue plugging in whenever you want to get electricity whenever you need. And I don't think that this will work for the transportation sector. So I think here we will really require at least some degree of behavior change. And so what we're trying to do and what we are using forecasting for is to make this behavior change as easy as possible. I just want to go on 2 examples where we use forecasting in our work, and one is for electric vehicles. So we think about everybody thinks about using electric vehicles to stabilize the grid once it is fueled by renewable energies, which are difficult to control. And so the problem is that for the owner of an electric vehicle, mobility will always be his first priority. So once you use his car to delay charging or discharge it to stabilize the grid, and he cannot or she cannot travel somewhere, she will opt out of this contract and no longer provide the electric vehicle for grid stabilization. And therefore, it's very, very important to forecast the usage of the electric vehicle of this individual person so that you can really get the most of this battery for the electric energy system. And the second one is ride sharing. So a major idea how to reduce the carbon emissions of the sector is to reduce the number of trips. So not only switching to electric vehicles, but really having having more people per car, and therefore having more cars, less cars on the road, sorry. And here it would be very nice if people would share rides. So the potential is gigantic to share rides, but at the moment it's very inconvenient for people to do so. So if you could really perfectly forecast their mobility, then it would really be easy to match their mobility needs and to pool them together. And so these are 2 examples where we need forecasts in the transportation and mobility sector. And the problem is that these forecasts are really, really hard because you're no longer forecasting a smooth group of people, but you're forecasting individuals. And then it gets very difficult. And that's what we hope that machine learning can help us.
Henry, we see gray boxes where there are Zoom windows. So if you could share, instead of the whole screen, if you could share just that application that you're using. You might have to stop sharing and start sharing again, and then click on the window that your presentation is in. Unless that's what you did.
Did you see nothing at all, or?
No, we could see most of the slides, so it was just a box.
Okay, well, then it's okay. I mean, I haven't really prepared slides, so if you saw the graph, then it's everything that was.
Okay.
Okay, so yeah, thank you very much. Yeah, thank you for the introduction. I guess we're ready to begin kind of group discussion now. So yeah, again, if you have questions for the speakers, please enter them into the chat.